This is the 8.1 quick check. I'd like to go over the answers. So the first test says, here are two beakers that represent the reactants and products in a reaction. Is this reaction at equilibrium? Okay, the idea here that it's a pretty common misconception that equilibrium is when the two beakers, when the reactants and products have equal amounts. So the real answer to this is maybe. Okay, maybe it's at equilibrium, maybe it's not at equilibrium. You really can't tell from the situation. So we really need more information about, the reaction rate and things like that. So justify your answer. There's not enough information to be able to tell. So this could be at equilibrium, maybe not. Okay, what is equal at equilibrium? Okay, the forward and reverse reaction rates. So the rate forward equals the rate of the reaction in reverse. Now, in the demo that we did, the amount of water transferred, that was equal, but we want to be a more generic answer. So the forward rate and the reverse rate, those are equal at equilibrium. Okay, constant expressions. So here's our picture here. We say, okay, this gas, gas, and gas. So the equilibrium expression, we're going to say Keq equals, now it's products over reactants, so concentration of NO to the fourth power divided by the concentration of N2O to the second power and the concentration of O2 to the first power. So that is the equilibrium expression. Okay, for the second one, we have a solid in there. So because there's a solid, that one is not going to be part of the equilibrium expression because its concentration really does not change very much. So CO concentration squared over CO2 concentration. And those are those two answers. Now next, given the following reaction, is this reactant favored, product favored? Explain. Okay, and the key is looking at the Keq value. Okay, and so it is definitely product favored. And the reason is that the Keq is much larger than 1. And that's why we know it's product favored. Now what does that mean? That means that if we had this at equilibrium, okay, we would end up with a little bit of our reactants and we would have a lot of our products. Now the Keq is, this number here divided by this number squared, and since it's much larger than 1, we must have lots of products. So we know that this is product favored. Now for every time an NO2 changes into an N2O4, there's an N2O4 that breaks up into two NO2s. So the rates of the forward and reverse reactions are the same, but the amounts are not going to be the same. For the reaction N3, H2, and NH3, the following concentrations are found at equilibrium, so we're given some numbers. Write the expression and find the value for Keq. So we'll write the Keq expression. Concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. So that's our expression. Now we're going to substitute in the numbers, and the numbers, for NH3 it's 0.30, and don't forget to square it, that's a molarity, over N2 is 0.10, that's to the first power, and H2 is 0.20, and that value is cubed. So it's going to be 0.3 times 0.3 divided by 0.1 divided by 0.2, 0.2, and 0.2. And the value we get, 112.5. Now these Keqs, these are unitless numbers. So the equilibrium values, these are equilibrium values, so this really is the Keq. Okay, so this is much larger than 1, and so we know that this is product favored. Okay, last question, and that here says, given this following reaction, is the mixture, if a mixture contains 0.5 SO2Cl2 and 0.1 molar SO2 and 0.2 molar Cl2, determine whether the reaction will proceed in the forward or reverse direction or if it's at equilibrium. Okay, we are given a value here for the Keq. Now notice it says at 100 degrees. We don't need that 100 degrees. That is just the proper way to say it because the Keq changes for different temperatures. Well, first step here would be to write our Keq expression. So it's going to be the concentration of SO2 to the first power times the concentration of Cl2 all over the concentration of SO2 Cl2. Okay, now that if we put in equilibrium amounts, then we're going to get the equilibrium constant. And we know that the equilibrium constant is 0.078. Now what we want to do is do the same thing, but this time we want to put in the concentrations that we happen to have, and that is not Keq. We're just going to call that Q, our test quotient. So our numbers are SO2 is 0.1 molar, the Cl2 is 0.2 molar, and the SO2-Cl2 is 0.5 molar. For this I get a value of 0.40. So we can see that Q is smaller than K. And since Q is smaller than K, then we can go back and say, okay, that the reaction is going to react. And here's one way to do it is to say, okay, let's say we have a number line. Here's Q, and K is larger. So therefore, the reaction is going to have to go in the forward direction. In other words, our reactants are going to have to turn into products for this reaction to reach equilibrium. So back here, determine whether the reaction will proceed in the forward direction or the reverse direction, or if it's at equilibrium. And the answer is it needs to go forward to reach equilibrium. So we're going to make more SO2 and Cl2 in order to get a number like this. And that's 8.1.